Hello everyone, welcome to Mutlu Learning Hub. Today's topic is regularization. Sometimes you train a model, you like the validation score, and then you retrain, and it feels like you build a completely different model. Same data, same code, different weights, different feature importance, sometimes even different prediction. That's what this video is about. This is not about squeezing out 2% more accuracy, it's about stability. It's about controlling variance, so your model behaves the same way when the data needs just a little. Here is the plan. First, why retrains disagree even when validation looks fine. That's the confusing part. Then, what regularization is actually doing to the model. And finally, L1 versus L2 and when you'd pick each, plus elastic net, which is basically can I get the best of both? Here is the situation. A model can fit the training set nicely and still be unreliable. If your data is small, your estimates depend heavily on which exact points you happen to sample. And if the model is flexible, there are many different parameter settings that look good enough on the training set. So validation can look fine, but when you retrain, the learned weights change a lot. That weight disagreement across retrains, that's the variance. Let's see the picture on the left. Tiny data set, same looking fit line, but a slightly different sample would push you toward a different best model. This is why people sometimes feel like modeling is random. It's not random, it's just variance. Let's make it concrete. On the left, we are retraining the same model multiple times. Look how wide the band is, the slope changes, the line shifts, everything is kind of wiggly. On the right, same data, but with regularization, the retrain fits are much tighter. They still vary, but they vary in a controlled way. And here is the important part. You can have the same average validation score in both cases, but one of them is much more stable. So if you care about real world use, track stability. For example, the standard deviation of validation score across seats or how much the coefficients drift. So far, we talked about instability across retrains. Now let's look at instability inside a single fit. On the training points, both curves might look fine. The overfit model bends to chase every point, and on the training set, that can look impressive. But the real question is what happens between the points where we don't have observation? That's where generalization lives. The regularized curve stays smoother. It doesn't react to every small fluctuation in the sample. It only bends when there is strong evidence. And that's really the idea. Regularization avoids solutions that depend on fragile details of the data. Here is the core idea. Regularization adds a small cost for complexity. So instead of saying pick the model that fits training best, we say pick the model that fits well and stays reasonable. Because with many models, there are multiple fits that look good on training. Some of those fits are extreme, and extreme fits tend to be fragile. Regularization nudges you towards smoother, repeatable fits, so the model is less sensitive to exactly which data points you got. Now, let's focus on L2, also called rich. The loss becomes the usual mean squared error plus lambda times the squared weight. What does that actually mean? It means we are still trying to minimize the cost, but now we are not allowed to let the weights grow freely. You can think of it like this. Without regularization, we just go to the lowest point of the loss surface. Wherever the minimum is, we take it. But with L2, we are adding a constraint. We are saying you can lower the loss, but you have to stay within a certain budget for the weights. That circle in the picture represents that budget. If the best unconstrained solution is far away from zero, L2 pulls it back. It prefers smaller, more balanced coefficients, and the size of that circle depends on lambda. If lambda is small, the circle is large, the model has more freedom. If lambda is large, the circle shrinks, the model is forced closer to zero. So L2 doesn't remove features, it just shrinks them. And that shrinking effect is what makes the model more stable. Now, let's talk about L1, also called Lasso. The setup is the same as rich. We start with the usual error term, like mean squared error. But now the penalty is the sum of absolute values of the weights. What that changes is the shape of what the model is allowed to do. With L1, the constraint has corners, and those corners matter because the easiest place for the solution to land is often right on an axis. And landing on an axis means one of the weights becomes exactly zero. So this is where sparsity comes from. Lasso can actually remove features not by manually dropping them, but because the optimization naturally pushes some of coefficients to zero. But here is the trade-off. If you have correlated features, meaning two predictors carry almost the same signal, Lasso may not pick them consistently. Across retrains, it might keep feature A in one run and feature B in another, because either one can explain the data almost equally well. So, Lasso is great when you genuinely want a smaller set of features, but with overlapping predictors, you get sparsity without always getting consistency in which features are selected. So, which one should you use? If you expect many small effects or your features are correlated, start with L2. It's stable and it behaves nicely. If you really need sparsity, maybe you want a simpler model or interpretability matters, or you believe only a few features carry real signal, then L1 makes sense. And if you are unsure, you'll probably end up at ElasticNet. Now, let's look at ElasticNet. ElasticNet simply combines the two penalties. We take the L1 term and the L2 term and add them together. So the model is still allowed to set some coefficients exactly to zero, and that's coming from the L1 part. But at the same time, the L2 part prevents the solution from becoming unstable when features are correlated. Geometrically, you can see that in the constraint shape. It's not sharp diamond like pure L1, and it's not a smooth circle like pure L2. It's somewhere in between, a rounded diamond. That means you still get sparsity in some cases, but the corners aren't as aggressive. The model doesn't flip as easily between correlated features. So in practice, ElasticNet often gives you a smaller model, but with more consistent behavior across retrains. Now, let's add a quick reality check. Regularization helps with variance, but that's all it does. If your model is already too simple, meaning you're limited by bias, adding regularization will just make it worse. If the underlying signal is weak, regularization can't invent signal for you. Another practical point, scaling matters. Regularization penalizes the size of the weights, so if your features aren't scaled properly, the penalty won't behave the way you expect. And maybe the most important one, if the real issue is data leakage or a bad split, regularization won't fix that. At that point, you are regularizing the wrong problem. So here is how we use regularization as a diagnostic tool. First, we look at drift. Do coefficients or predictions change a lot across retrains? Then we compare runs across false and seeds, not just the mean score, but stability. And then we decide, do we tune lambda, simplify features, or do we actually need more data? Because good modeling is controlled experimentation, not just train once and hope. And that's regularization. Thanks for watching. See you in the next one.